because it will stop when it hits the building, right? You would not, you could use, I mean, normally that's what happens, right? You can use your phone indoor without having really a like infrastructure inside, so you can use your cellular network, but that's probably not the case if you use millimeter wave frequency. So you would have to think of, in a sense, another tier of millimeter wave base stations inside, in this case. Okay, that's kind of the assumption behind this project. This is a project we do in collaboration with Belfast University, Queen's University Belfast, and Virginia Tech in US. So it's a US-Ireland collaboration program. Okay, so ideally you want to serve things like, again, for example, concerts, you know, very crowded shopping malls. So these kind of situations are you know, the target, or possibly you know, stadiums, stuff like that. Okay, maybe, you know, you have a stadium with a cover, right? So, and then again is the similar story. One thing you have to be a bit careful is to play with the realistic assumptions. So I think we are not thinking of something like, well, probably it doesn't even make sense, but we are not thinking of an indoor environment with a very high mobility. So even a very frantic you know, mall, not sure if that's really something we can cope with. I'm more thinking of stuff like concert halls, movie theaters, stadiums, because in that case the people go, sit and watch. They do not really move around, right? So you know where they are with their phones, right? So that's probably more realistic as a case study, as a use case, yeah? Okay. So what we do, well, you have to make some assumptions, of course, to, you know, to get the work going. So we assume that the access points are mounted on the ceiling, and they illuminate a spot. It's like a spotlight, right, on the ground. We assume a grid pattern deployment. You can do more complicated things, but we started from that. We have some model which we take from literature about body attenuation. Roughly speaking, every time your signal hits a human body, it attenuates by 40 dB, which is a lot. So essentially, when you hit the first body, you're already done and dusted. If you hit another one, gone completely, you know. So, but it's already very detrimental the first time your signal hits a body. Okay, so that's a big factor we are trying to study. Yeah, of course there is possible interference between access points, especially if you because one degree of freedom you have, one design parameter is how dense or how, you know, sparse is your deployment, right? If you want to, let's say, follow user better, then you have to have a dense deployment, but then you start to have to cope with interference. So it's never a free lunch. Even though it's millimeter wave, still within some range you start to you know, perceive the interference from the neighboring access points. Yeah. Okay. Yes. So other things you can play with are the beam width. Okay. How narrow or how, you know, broad is your beamforming beam. Okay. Yeah, and we try to see what happens to things like throughput, coverage, if you have this kind of deployments. You can have more complicated models, okay, but what we did is a simple model for the radiation pattern, where you have like a main lobe and the secondary lobe. Secondary lobe is weaker, of course, in terms of power, but you know, we play with the main lobe in terms of the beam width. So the narrower the beam width, the more power you can transmit in that direction, right? You kind of, that's the point of beamforming, actually. Okay, so that's really what we do. So there is something in the model also taking into account the body, okay, because the body is the main, the body blockage is the main aspect that we want to study here. So we want to see how the user body shadows the signal. And there is some, I mean, I explain them better in the paper, but there are some geometric considerations. For example, is the mobile phone in your pocket or do you have it in the hand, right? So this kind of thing matters because you see, let's say I have the access point behind me. Okay, there is some geometrical consideration to take into account, because if the mobile phone is too close to me, it's not going to see the access point, right? So if it's here, maybe then I will have access to the signal, right? Orientation, of course, you know, if I am facing the access point, well, pretty much, you know, a good situation. But if I start to turn more and more, the signal will drop, right? Because if I am again in between my phone and the access point, I cannot access the signal. It also has to do with the you know, basically person complexion, right? Because if you have a child, it will block less, right? The child will block less. If you have a, you know, a bigger person, of course, it becomes like a bigger obstacle. So all of these things we try to capture in some models. So you have to play a bit with trigonometry and so on. Okay, but eventually you can model this kind of things. So the simulation setup is pretty much like regular, as I said, deployment. We do not assume any corridor or indoor wall. It's an hexagonal deployment. The access points are fixed at a certain height. That doesn't have to be the case. Of course, you can start to play with that too, right? And so if you go higher up, you can cover more users, but you start to interfere more. If you go down, the other way around, right? So it's another degree of freedom. It's similar to play with the height as playing with the beam width, if you want. Okay, you can play with the density of the access points. That's another thing you can do. Yeah, and we do not play with adaptive antennas, smart things. So it's just, you know, we have a fixed beam pointing down. Now, one of the rationales behind this project with Virginia Tech and Queen's University Belfast is that we want to keep it simple. So from the beginning, actually from the project proposal, we said we are not after massive MIMO here. So this is something pragmatic that should work in, you know, a reasonable amount of time. So pretty much right after we are done with the research, should be possible to implement some of this. So there was kind of, you know, consensus that this should be practical. Okay, so we do not have crazy assumptions. We do not have base stations moving around. We do not have very adaptive things. We do not have a lot of antennas. So this is something that possibly, you know, is not too far-fetched. Now, the UE the user can associate in different ways to the access point. It could be the closest one in terms of Euclidean distance, but it could also be the closest one in terms of electromagnetic distance, the power, right? So, and from what we can see, it's way better if you associate with the strongest power, as we might guess, right? So the distance doesn't really make a lot of sense. Also because, you see, if you are associated to the closest access point and this access point is blocked, is of no use to you, right? So clearly power is a better metric for association. Okay, so we basically studied the signal to interference plus noise ratio, and we use that to compute coverage, which is essentially, for us, is the percentage of users that are having a SINR better than some threshold. You can change the threshold, of course. The area spectral efficiency is like so we average over all the cells in the system, and for each cell you have the logarithm of 1 plus SINR in the, again, average, okay, and then you divide by the cell area. So this is the bits per second per hertz per square meter. What can you change? Well, in this model you can change, as I said, the intersite distance, so the access point density. You can change the beam width with which you illuminate the area. You can also change the position of the user with respect to the body. Okay, so is it more far away? Is it closer? Yes?
The simulation setup, the platform is
I think, recollect, there's a guy, it's probably MATLAB, I think. Probably MATLAB, yeah. It's like the, this is the person actually working on that. Because it's a MATLAB script, yeah. Yeah.
Say access point density will be depends on the user density. For this, like that relation is like.
Well, what we did, I don't think, I have to recollect actually the results. I think we tried just to have, just thinking in terms of the user density. I don't recall actually how many users. I don't think the focus was much on having too many users. It was more studying the impact of. So what we did with this model. So you have a user, okay, which is being served, and then I can't recall now how many users we decided to have per cell, but I don't think the focus was much on that part of the study. But you're right; it should bear some relation.
If this is the case,
Yes.
then every time it is not practical scenario that every time there should be same user density.
Yes.
Okay. It may vary with time.
Yes.
Because sometimes there will be more
Correct.
dense area, sometimes there
Correct.
will be less dense.
Correct.
So like I am thinking that it may happen that depends on the user density. This AP can be switched on or off, such that the energy savings can be done.
Correct. No, I think you're right. I think especially if you start to have too many of them,
Yes,
many access points, then it makes sense. Yes.
because we every time we don't need such many type of
Yep.
such many number of access
Correct.
points.
So then you have to also detect how many people are there per unit square or
Yeah,
whatever.
yeah.
And that detection could also
And
be
at
done.
most how many number of people can be served within one access point?
Now, about the detection of the density, I mean, I was discussing with some people recently. It seems not to be a very complicated thing to do. So what you do, you have basically every user that will transmit will increase the level of power. So you kind of measure the aggregated power. So you kind of see how many are there. Okay, so that.
Sensing and then.
Yeah, you pretty much really measure the receive power. Okay, so and I mean, I also didn't know about that. So, but I was speaking with the radio engineer, so no problem, that we can do easily, even with macro base stations. Okay, so you kind of know what is the power, so you just sum, right? So yeah, so of course, I mean, this is a starting point, and you see in this case the focus was more on performance analysis. But of course, we didn't really tackle yet the resource allocation part. So what you're saying is like a resource allocation problem. This makes sense. I think you could play with energy efficiency and stuff like that. Of course, you have also to have a mechanism in place to actually see when it makes sense to switch off and coordinate, right? So that might require a bit of overhead in terms of coordination between access points. But yeah, it is a problem that I think people are interested in. Okay, like the energy aspect. And it's also a way to control interference, right? You might actually have to switch off some base stations to limit interference too. Yeah.
Are we thinking of energy harvesting anytime?
It's probably, I'm not aware, but there are probably works that are working there. I think that there are works on energy harvesting for millimeter wave.
What she's saying
Yeah.
makes sense, because if you are sensing and if you are directing your millimeter wave accordingly, if it is not used, then you can use it in energy harvesting.
Right. Yes, and again, energy harvesting is normally good because you can actually use interference to your own advantage. That's another good point, right? So I think these things make sense. I suppose in general it's another way to become I think especially if you have like ad hoc deployments, these kind of things, then it's probably a good idea. I think energy harvesting has become immensely popular in our community, so I wouldn't be surprised if there are people working for millimeter wave in that space. I'm just not aware myself, but there are probably works. Yeah. Any other question, comment?
Sir,
Yes.
other way.
Yeah. Yeah. Then, yeah.
So actually blockage for MM wave compared to microwave.
Yes.
So can we say that it is more safe as compared to microwave, or is there any impact on body as the frequency is increasing?
Yeah, that's a good point. Actually, it's one of those topics that normally communication engineers tend to sweep under the carpet, but it's a very valid point. I think I don't know if there is really any consensus about the harm that radio communication does on the body. You know, I don't think there is any conclusive study as far as I know. I know people now and then you know, keep on raising this point. In essence, I mean, the good thing about millimeter wave, you are very directional. So probably, well, you get a strong signal toward you, but probably less from the environment, I suppose. Okay, the fact that you are getting blocked by others, by other things, again, you are exposed to less things. But you know, probably a physician would tell you what the impact is. I can't comment on that. I know it's something that you know, people. I don't think it's part of the mainstream discussion. That doesn't mean it's important, you know, because it is, especially since we are increasing the number of transmitters everywhere. It is probably something that should be eventually considered. I think there are inconclusive studies. Some people say that continuous exposure to EM radiation might be harmful. Some others says no. So I think science, I mean, the only thing I can tell you, my opinion as a scientist, I don't think there is conclusive evidence. That doesn't mean it's a yes or a no, right? So yeah, I think something to be considered. Clearly, too high power exposure for too long time might not be too good, in my opinion, right? It's like you start to when you use the phone on your ear, you start to see it heats up after you use it, right? So I mean, something is going on. Now the not the millimeter wave, but the terahertz frequencies are considered, as I told you before, by these nano network guys. So it's one of the ways they think of conveying information, for example, inside human bodies for medical applications, diagnosis, drug delivery, this kind of thing. So one is that. Another one is to engineer the molecular communication already present in the body. For example, they do some. They are thinking of doing some bacteria engineering. So they use actually the biological entities to convey. So these are the two ways. So they are using it now. To be fair, I don't know if they tested this on people. I doubt it. There are ethics issues, right? And but again, that literature for terahertz so might tell you more about what they think about you know, human body impact on human body. I'm just not an expert. I don't know if anybody else knows more about this area, about the impact on health and human body.
It does have a, I read a paper
Mm.
where, I mean, of course, we are all electromagnetic human beings. We have
Right.
radiations of our own. There was a very small and insignificant work on the interference of our electromagnetic radiations with that
Right.
of the radiations. It was very insignificant, but although they have said that there are impacts.
Yeah, I think, you know, it's again, it's probably something that is being monitored. I think it's fair to say. I think, you know, there is some people check these kind of things, I suppose. Okay, so it's I think, again, for some reasons, probably because it's more of a medical question, it's not really been a part of the story. Definitely interaction of telecom and healthcare has been there for a while, right, as a tool. But what the tool does to health, that's much less explored, definitely. Okay, that's what we can say, I guess. So I wouldn't know if millimeter wave is better or worse. The fact that you absorb it doesn't mean it doesn't hurt you, though. It hurts less other people, right? But the first guy is still experiences, so I don't know. Yeah, and power-wise, you are doing power, which is power transmission, which is focused. So it's a beam. So again, I don't think you're probably experiencing less. It's just probably less people. So in that sense, it might be good. So less people at any time would experience it, but those people still do experience it, right? But yeah, it's difficult to say, you know, without having a proper scientific study. Yeah. Okay. So, I think they are not talking about any difference in that sense. They're still talking about the same powers. I think, yeah, I don't think they're using largely different powers, because essentially the thing is that you compensate the loss with being more directional, but the transmit power, I think, is probably the same. Yeah. Yes.
In the case of indoor scenario, because millimeter wave is mostly applicable to indoor scenario,
Yeah.
let us think about any cinema halls
Yes.
or stadia.
Yeah.
So mostly what happens, the level of seating is not safe.
Yeah.
If access points is detected in the roof, then what happens, the uppermost seat will get the will act like a closer user.
Yes.
Comparatively the lower.
Correct.
So is it is any provision is like that, depends on the seating position, we can vary the power such that
Sure.
maybe fair, or we can include any fairness type of criteria.
Oh yeah, you could. You know, as I said, I mean, it's something we didn't investigate. I think there are some good. I could actually suggest some good work on MAC and resource allocation problems. That some people are looking into that. I think I mean, we do a bit of this story, but it's really a bit more theoretical, like trade-offs, stuff like that. I think we are not so much in this project at the moment about designing resource allocation schemes, but it's definitely relevant. One thing they try to do, I mean, the idea is also to blanket kind of the space so that you are always close. So probably, you know, it's not that you have to play too much with power control in the sense that you are possibly always very close. So, and you have kind of your dedicated access point, sort of, but if you have less access points, then you have to start to play with what you say. Yeah. So there is actually, we are doing good with time. So there is actually, I have some just, you know, snapshots of what we got. So what we are showing here is actually the coverage on the, no, these are the second one, is the spectral efficiency. Yeah, so the coverage is on the left hand side and the area spectral efficiency, so basically the throughput per area on the right hand side. So what you, first of all, and then you have the inter-site distance on the x-axis. So what does it mean? It means that if you go toward the right, you have a more sparse network. Say if you have 100, it means it's half, so it's every access, I mean, an access point would be 200 meters from the neighbors, okay, in this regular deployment I showed you before. If you have 1 meter, of course, they're very packed, okay. So what happens is actually that if you start to change the inter-site distance, and let's say you fix a certain beam width, 41 degrees, so to speak, so what you see is, for example, cyan line, this kind of bluish line, right? It does something very weird. So it goes up, maximum, goes down, almost to the minimum, up again, and then down again. It's not really something we would have expected. So there is actually an interplay between the cell size and the beam width. So the beam width will imply some actually area which you cover with your transmission, but then if you start to have, you know, for example, if you start to have too large a cell and you have a fixed beam width, you have a lot of users that you're not serving, yes? And so that is what happens actually when you go toward higher distances. So toward the right, you see there is a trend generally that is decreasing because of this. If you go too actually much on the left, what happens is like you have a fixed beam width, right? And then you start to have smaller and smaller cells. So it means that everybody is interfering with everybody, right? So you have a situation where there is a lot of interference, a situation where there is a lot of on the left hand side. On the right hand side, a lot of the area is not covered. So the best match, of course, is when you are in a sense matching the beam width with the cell size, okay, with the set of users you serve, because that's the best thing you can do. It's kind of you could think of it as like you are covering your area with circles, and it's a kind of sphere packing problem, right? So you're kind of doing the optimal beam width and cell size design in that case, okay? So you have actually these things that play a role, and you can't have a beam width that works best because of this reason for all the densities. So what we show here, you see, if you use different colors means different beam widths, so they are all going to do different things, and they might be optimal for some region of the density, but not throughout all the regions. So you should actually, so these black circles are the best value you can get scanning through all the possible beam widths. Okay, so this assumes if you want to achieve this kind of envelope, this top line, you would have to have an adaptive scheme that picks that picks the best beam width according to the density of the deployment. Okay, but if you are given a certain deployment density, then there is only one beam width that is the best one. Okay, so let's say if you don't assume any change in the density of the deployment, you will have only one beam width that is best for that, right? Which is when actually the beam width matches the density of the deployment, which makes sense. Okay. Now, what works best for coverage doesn't work best for throughput. We know that there is a trade-off between throughput and coverage, right? So essentially, you see, I've been plotting here the same values of beam width we use to get the optimal curve for coverage, and it doesn't show to be optimal for area spectral efficiency because, for example, using those values doesn't give you the optimum here, right? You see, you have this blue curve is doing better already, right? So you would have to have a new set of optimum values here if you want to get the top curve, the top envelope. So the message here is like, yes, intersite distance matters, but it also matters what you are after. If you're after coverage, there is going to be an optimum beam width. If you're after area spectral efficiency, there is going to be another one. Okay, and these are for users that are, okay, the access point is 10 meters above with respect to the ground, and the user is in the hand 30 centimeters far away from the body. Yes? Okay. And this is a very complicated plot, so I'll try not to, I'll try to maybe guide you quickly through it. So you have, here we put both area spectral efficiency, y-axis, and coverage, x-axis. Okay, so what do we have? So basically, this situation here is actually when, let me see if I get it right, the user is in the hand, user is in the pocket, it's trying to find out, yes. So I think the user in the pocket is this bluish curve here. Okay, so what do you have? You have actually, if the user is in the pocket, if you want to go for very high spectral efficiency, so you are in this high region of the y-axis, you have to compromise with coverage because it's about 60%. Okay, here, kind of. On the other hand, for the user in the pocket, which is again this kind of bluish line here, you would have that you can increase coverage, but then you are going down, right, with the spectral efficiency. Makes sense. Now, this other bunch of curves here are when the user is in the hand, except for the green one. The green one is no body attenuation. It's kind of a benchmark. Okay, the green one means nobody's there. So it's a vertical line. What does it mean? It means that you have, well, it's essentially making the things independent of each other. Okay, you can just say, okay, I'm going to use, you could basically, you see, it doesn't really make much sense. It's a vertical line because it's kind of an ideal case. So we are not really, focusing on that. But basically, these other, let's say, orange, yellow, and kind of purple lines, they are when the user is in hand. So this orange line is when the user is, when the phone, sorry, is in the hand. So the user is 5 centimeters far away. So I have it here. The yellow line 15, the purple line 30. Okay, so what happens is the more far away you are, in a sense, the more you go toward the ideal case, which is making sense because basically that's where you have the least impact of blockage, at least your blockage, right? And by the way, your blockage is likely going to be the most nasty one because you are definitely the one that is messing up more between your phone and the access point, right? And the attenuation is so big that it's enough to have one body to kind of kill the thing. So it's more likely than not that you are the body yourself, you are the body blocking the communication, right? That's why if you just make sure that your phone is a bit far away from you, it kind of goes toward the situation where nobody is there at all because of the model we are using. I think it kind of makes sense. Okay, and another thing to say, what? Let me see. So for this, let's say this part of the plot is for high densities of deployment where a smaller beam width would work better, because if you have a high density you have to be careful not to interfere with the other access points. This lower, let's say, part of the curves is for lower density where actually larger beam widths would be better, because if you just are too narrow you are missing out on many users. So you have to, that's kind of what you have to play with. If you have a packed deployment you have to, yeah.
So your beamforming according to the
Yeah, it's not really that, it's like more we are collecting, you know, the results. We are not doing any adaptation or anything. This is just, it's kind of, you know, we give you some guidelines. So it's like more an input if you have to design an adaptive scheme, yeah, but we are not doing that. So, yeah, that's pretty much it for this. I don't know if you have any questions. So we are doing a bit more of work on this. We're writing a journal version. So what was missing here was the fast fading. Okay, because I mean the users are not moving fast, but we know that there is this micro mobility effect. So you do have to incorporate that too. Okay, this kind of multipass due to small movements, and that's what we are doing right now. And another step, I mean, other two things we are going to do in the next couple of years in this project. I mean, we are definitely going to do some resource allocation. Okay, that's something we are planning to do, and then we are also hoping to kind of validate these results with experimental models. Okay, there is a good group in Belfast. They are actually characterizing channel based on real measurements, and hopefully we will be able to plug in their channel models and see how that changes the picture. The first evidence we got complicating the model, at least theoretically. So even adding fading, yes, it changes the picture, but not so much. Okay, it seems to me that still, because of the attenuation thing itself, path loss is really the important thing. Okay, way more probably than for microwave. So it seems to me that that's really the most important thing, at least as a general message so far. So path loss and shadowing, of course. So way more the long-term fading than the short-term fading plays a role in millimeter wave, seems to me. Okay, that's the indication so far. Another question? First, second, yeah. No, yeah.
Since the cell sizes are going to be so small,
yeah.
What about the overload of handoffs? I mean, it would be tremendous.
Very good question. I think you're right. That's something that would limit in the end the density. You do have to track users even if you don't do handoff, because if the user moves around you, because it's been forming, right? So you would have to do, it's kind of what they call, it's kind of chasing the guy, right? So it's what they call soft handoff, softer handoff, right? Within the cell. So that is already there. Plus, if you move around, I think you're very right. That's why I think we are thinking of scenarios that are more static, honestly. Okay, I think I don't see this honestly happening with drones. No, it could be again if the drone is, let's say, possibly if the drone is kind of the base station, maybe it's kind of redeploying the base station. That might make sense, but with users, I don't see that honestly. It's too much hassle. Even if that was the case, let's say you are given a, it depends also on what, let's say you are, also for researchers, there is a sponsor that wants some work done. So if you are given that crazy project for some reasons that escape me, probably you would have to move away from centralized optimization for sure. You would have to do things that are more of a distributed nature, right? Maybe some kind of suboptimal heuristic thing. You wouldn't have the possibility to really, have a central optimizer. That's not feasible at all. But I think there are also limitations in the practicality of things. And I think if the overhead starts to become comparable or equal to the actual bandwidth, what's the point? You are designing a network to understand the environment, but you're not using it, right? So then, of course, it's already with massive MIMO, people are a bit doubtful because half of the time you are estimating. Because you have so many links, right? That it's shown actually you need about half of the bandwidth just to do the channel estimation. So there is a price to pay for being, that complex in your technique, yeah.
So have you considered any arrival rate or distribution of the arrival?
Arrival rate, not in this work. So you mean like something like Poisson or stuff like that? Yeah. Yeah, no, we do have other works. I didn't include them in this course about wireless caching. In that case, of course, it's something you consider. Here we didn't know.
Because it may have any effect in the admission control algorithms and all the scheduling
Yes.
or queuing models.
Yeah, no, of course. I mean,
On the arrival, all
yeah.
these things will change.
I fully agree. I go back to what I said before. So we didn't really do work on resource allocation so far. For that, it's relevant. Yes. Right now, it's pretty much what we did. Okay, before we even start resource allocation, we want to understand. This is kind of what I think is the practical engineers call a sensitivity analysis. You want to see what matters. Okay, because if something doesn't matter, you shouldn't have it in your resource allocation problem in the first place. The trade-offs, right? What do you have? So what are the knobs, so to speak, right? And what are the meters? And is there any pattern, any relation? Once you have that, which we kind of have now, then you move on and you use this to inform your resource allocation. So then you can complicate the model. I think you're right with Poisson and other things. One thing we are doing though is Poisson in space. So I didn't show it here. We have like it in this work going on where actually the base stations are deployed according to a spatial Poisson point process, right? So we use some stochastic geometry. So that's something we are doing, not on the user side though. I mean, at the moment, yeah. Not at the moment, no. It's just they are randomly deployed now. That's it. So they are, but we don't change the number. We don't change the arrival rate, yeah.
Another thing, sir,
Yep.
The outdoor path loss model and indoor path loss model will change because
Correct.
in case of indoor we have another factor that is wall penetration loss.
Yes.
That will add up.
Yes.
So we need to have some concept of dual path loss model in
Correct.
this case, right?
Absolutely. I'm going back to this, not for millimeter wave necessarily, but for in general. I have a lecture next week. We are going to talk about this dual path loss aspect. It is something important, and they it essentially becomes like like a Bernoulli kind of distribution. So you have one option or the other with different probabilities. Actually, there is a model in 3GPP about that. 3GPP has this model where you have basically a probability that depends on the distance to be in line of sight, and you have 1 minus that probability to be in no line of sight. It's a very used model in 3GPP, very good actually. So I can give you some details if you want. Yeah. And I'm not aware of. Actually, there are works in millimeter wave doing what you're saying. Yeah.
Some paper of Professor Rapoport, I guess.
Yes, those, and I think
Called about phantom cells. They
right.
call some two-tier concept of.
Yeah.
They use one path loss model in another
Yeah.
some upper tier and one path loss model in the another tier.
Yeah.
So they call it
No, yeah. I think also in millimeter wave you have work from Robert Tith. They are doing like this kind of dual models. Yeah, so it's definitely something that you could consider. Yeah. Any last question?
Variable antennas.
Hmm?
Couple it with variable antennas to reduce losses.
Yeah, you could. I mean, variable. You mean in terms of aperture or?
I think wearable antennas, right?
Ah, wearable. Oh, sorry. So I understood variable. Yeah, definitely. Yeah, it is. second session of today. So essentially we reached halfway. So today we are going to complete module 2. So there are 4 modules. Of course we are halfway through. And this afternoon there is a tutorial at 4:30. So we are going to do like last time. So we have a paper club we'll discuss together. Okay, so I'm going to talk about full duplexing in this last bit of module 2 about physical layer technologies for 5G. Okay, just a reminder to ourselves that basically to make it a success story, whenever you have a communication technology being proposed, you need 2 things. You need the technology, yes, that's what this course is about, more or less. But then you also need an application. So the things might change radically depending on whether you have the application or not. Honestly, being a communication engineer, I'm not too concerned about the technology side. There are challenges, but we invariantly sort them out if you just give us enough time and resources. The market case is another story altogether. And for example, I already told you that 2G was a very good match. Was the story of a very good match between technology and the service you are targeting. Not necessarily so for 3G. 4G better, I think. And 5G should also be remembered in this lesson. Okay. One thing that I see is changing in 5G. Is that up to 4G, I think it was kind of clear the use case you had in mind, which was essentially smartphones, okay, pretty much. And all the story of 2G, 3G was really about cellular phones better and better in capability, okay, more or less. 5G is different, okay, because you start to have other things that have nothing to do with cellular telephony per se. So it's a bit more complicated to think of a general use case. Now, this has repercussions in the technology. That's why, compared to the past, we have such a big variety of techniques. I'm thinking of the example of waveforms. In 4G, it was pretty much working all the way on FDM or variants of it. I didn't really see such a big fuss about waveform back then. Today, it's a different story. And even honestly, the MIMO story was pretty much, 2 or 3 techniques. Nowadays, again, you have a big array of things and, many more things. So I gave this kind of course the first time in 2008. It was, I think, the University of Kolkata. And it was totally the 4G time, okay, and I do not remember such a big variety of technologies. Definitely it wasn't like that, okay. So I think there is, of course, because I mean the services we are targeting are very much heterogeneous in nature, okay. So just a reminder about what we are about. What are the KPIs we are after, okay? This is good also to have a bit of a recap because we are close to the half of the course. Okay, so we are about increasing the capacity in our system. It's essentially how much traffic we are serving, okay, in the system, how many users. We are about increasing the data rate. So here they have the example of remote surgery. It's one possible application of high data rate. But we are also about increasing the peak data rate, okay, and that could be where millimeter wave, for example, comes into play, where you need really a big, amount of data being transferred in a limited area, for example. We are about definitely pushing in, along the direction of energy reduction. The more and more we add nodes and capabilities and subsystems to the communication network, the more and more we have to consider the energy aspect. So one thing that has, I think the green story has been there more or less since the beginning of wireless communication, because it's a fact. You're not cable, so you have to be a bit aware of the energy aspect. But I think what has changed probably in the last few years it's not just about becoming efficient with the power you have, it's also kind of harvesting, collecting the power you need. So there is an interplay between, for example, renewable sources of energy and the way you use that energy. That wasn't there in 4G, okay? The best, I mean, when you were talking about green communication in 4G, it was about essentially being power efficient. This is not the case today. So you do have, again, other fields like energy engineering that are coming to talk to communication engineering, right? So that's news compared to 4G. Latency has been pushed to the extreme, so to the point that honestly physics will tell you enough, and then you have to come up with other things. That's where, for example, the paradigm of caching, storing, and possibly predicting things with AI might play a role. Yeah, if you can't be as fast as your opponent, you have to anticipate the opponent's moves, right? That's a lesson we know from strategy in general, right? So that's probably how you can gain time, right? And spectrum efficiency has to be pushed again, so that's a bit challenging because you see, increasing throughput, in a sense, you could also be about squandering resources. You just collect a lot of channels, right? Stuff like that. You can use a lot of power, you know, and so on. But spectrum efficiency is a bit more picky as a metric because it has to, you cannot really use more spectrum, and you have really just to become better with your signal processing and your technology. Okay, so that's the way you actually increase these. And again, you know, now we have hundreds of antennas, very fine coding techniques, very fine multiplexing techniques. So how much more can you push spectrum efficiency really? Okay, I don't know if you really can do much more with radio technology, honestly. Maybe yes, though. One thing you can do is full duplexing, okay? Full duplexing is about, now in the 5G jargon, because full duplexing has been there forever. It's like normal phones, right? But here we mean something specific. So we talk about half duplex when you are duplexing your uplink and downlink using either time or frequency. So you are dividing the communication using the time or frequency dimension. So you will have a channel in frequency for downlink and channel for uplink, or a time slot for uplink and a time slot for downlink, right? That's what we mean by half duplex in this context. Full duplex gets rid of that. It tries to actually send and receive at the same time and at the same frequency. That's what we mean in this case. So there are problems. We're going to see some of them, but let's say the problem is that you can actually target many of these things I've been talking here, because you are kind of speeding up things quite a bit, right? For example, you could double spectrum efficiency suddenly, because you have, let's say you have a symmetric communication, right? So you are sending as much as you are receiving. If you do it at the same time, same frequency, of course you multiply by 2 the spectrum efficiency, right? Makes sense. Same with latency. You don't have to wait for things. For example, let's say you have a cognitive radio network. You could use one antenna to receive sensing and one antenna to transmit without necessarily having to wait or to use more channels, right? So these things are good. Relaying, you can actually have a constant flow of information over time and frequency. You receive and you forward at the same time, right? These are all applications where you can see the power of full duplexing, I think. Of course, you have other issues which have to do with interference mostly. You have a whole set of new interference situations which weren't there before. So before, let's say you assume cells to be synchronized. So if it's downlink for everybody essentially. So if I'm transmitting in downlink to a user, the only source of interference are other base stations, right? But if you now have this paradigm where you don't have necessarily to split the communication downlink and uplink in time or frequency, everything happens simultaneously and over the same channel. What does it mean? If you take this downlink example, it's not just downlink, it's also uplink. So I will have interference from what? Again, from the base stations, but also other users, right? And even my own, if I'm talking now uplink, even my own base station becomes an interferer, right? Because it's kind of a self interference situation. So a thing that has emerged is the need of successive interference cancellation techniques. You need to subtract interference to get something out of it, and again, though, there are some limitations in the capability of what you can do, but they are very powerful nowadays. So they have the capability to cancel up to 180 dB of interference. Okay, so that they're getting better and better. But all I'm saying is here is that this ×2 spectral efficiency gain or delay reduction, whatever, is nominal. The actual value is less. Okay. So this slide I think I already showed is just to again put things in context. So you see the first column is actually duplex mode, and this is a presentation from Rode and Schwarz. It might be random, but it's also kind of significant that the first one that appears is duplex modes. I think it hardly gets any more fundamental for communication engineering than duplexing, right? It's one of the first things you have to decide. For example, historically, cellular networks are about FDD, and TDD didn't really play such a big role as far as I know, okay, at least from in the recent times. But there is also a good point for TDD, as we saw in this course a few times. So for example, massive MIMO, right? The fact that you have to estimate so much information about the channel links makes it inefficient if you have to design a frequency channel for that, which is the FDD thing, right? You would need another channel to feed back the information. TDD is a better deal because if you have an environment which is kind of static, you can assume the channel is the same between downlink and uplink, so you don't really have to feed back anything. You listen and then you use that information. That's it, right? So you can use the estimate you get in uplink for the downlink. That's the main reason why massive MIMO goes at the moment hand in hand with TDD. There are some people working on FDD to make it compatible mostly with LTE networks and so on, but I think it's still not so mature. So still it's kind of TDD the assumption. TDD, as I said before, is a good thing also because it plays with time. So hardware-wise, it's less complicated, the story. You don't, even when you get the spectrum from the regulator, if you have the FDD, you need a couple of channels because you will need one for downlink, one for uplink. You could get away with just one channel in TDD. So also from regulation viewpoint and auction and so on, if you have to get the spectrum, it's easier. Hardware-wise, it's easier because you are just switching on and off with TDD, really. With FDD, you need RF chains, right, to do the thing. So, and it's not so flexible. TDD, let's say you want to change the ratio between downlink and uplink from 50-50 to 75-25%. Well, you just transmit longer in downlink, end of the story, right, and shorter in uplink. With FDD, you would have to change the bandwidths, right, and it might not be so easy to do this, and you might not have the flexibility to do this. Another reason why FDD, well, so now you might ask, okay, if TDD is so good, why did they do FDD in cellular networks? The main reason, I think, is because the traffic is kind of symmetric. Okay, the technology was there, probably, it's like something that developed well, but the traffic is symmetric, so you don't really have to bother about this variability of the downlink uplink ratio. It's kind of sort of the same, at least it used to be, okay, with voice communication. So that's why FDD is good. Okay, you have probably the same bandwidth for uplink and downlink, fine. If you start to have situations like though, data generated by users, so you might have situations like maybe where the uplink is heavier than the downlink, or vice versa. If you start to have people watching streaming, it's the other way around, right? Or you might have new technologies like IoT, where clearly it's more uplink, much more uplink than downlink. So in that case, FDD, okay, you could still say, okay, I'm doing FDD and I get a bigger channel and the other is small. Yes, but this is not that this traffic is, the ratio is carved in stone. Once you have variability, you have it, right? So you might need to tweak things, and that's why TDD is being considered. I can't comment really how much it made it into the actual system implementation, but at least I see a point for it, okay? And this new, what I was saying, this license spectrum sharing regime They basically are also considering TDD, especially in US, especially when it's coupled with small cells. Why? Because small cells, you see, it has again to do with the variability of the traffic. So in a macro cell, a base station is serving, say, 50 to 100 users. So if a user leaves the cell or joins the cell, no big deal. It's kind of the same, right? It changes 1%, 2%, okay, of the load. So not, but in a small cell, maybe you're serving 3 users. A user leaves. There's a dramatic change in the load, right? Everything is relative. So if you go from 3 to 2, you lost 33% of the load. If you have 2 and 1 joins, you gain 50% of the load. Right? So that's why TDD is being considered for small cells, because it kind of makes some sense. Okay. But again, flexible is about flexible duplex here. They mean you could have like a system that adapts, right, the ratios between downlink and uplink, stuff like that. Or maybe using combination of TDD and FDD. Full duplex is different. They get rid of all this thing. They say we don't care even about the concept of downlink and uplink separation. We just do it together. End of the story. End of the problem with duplexing, right? In a sense. Now, theoretically, of course. Then practically, it's another story. So a bit more of details about the just visualization. Okay, about the half duplex technique. So, of course, in TDD, you are dividing your uplink and downlink over time. So in this, essentially, you are using all the bandwidth you are given for communication. In FDD, you are simultaneously doing downlink and uplink, but you are using different channels. So you have to split the bandwidth, right? Problem with both is that in the first case, you are not using, so let's say if you consider the system-wise, so what happens is like, let's say I'm focusing on downlink, I have to compromise. At some point I have to, I can't use it in TDD, for example, I can't use it all the time, right, the channel, because at some point I have to hand over the channel to the communication channel to uplink. Same with frequency, though in that case I cannot use all the bandwidth for my links, but I have to share with the uplink, right? And that's the problem of spectral loss, right? Because if you could possibly do them together, then you don't have this issue, right? You are using all the resources all the time for uplink and downlink, basically. Another issue with that leads to spectral loss with FDD and TDD is that you need guard bands between downlink and uplink communication to avoid interference, and that is true for FDD and for TDD. Okay, you need to make sure that the downlink communication is over before you start uplink and vice versa. Yes, it's like having multi-user interference within single user communication if you want. So you're trying to avoid interference, right? Yeah, and here they just show a visualization of, for example, if you have a much more downlink system, you see they're using many more slots for downlink. It could either be, I think here they mostly mean TDD, but you could also think of it as FDD, where you give a larger band to downlink in this case, or uplink. You can actually play with these things, and some people are working on more flexible duplexing techniques. Okay, but again, full duplex is a different story. So you see here are some possible examples of things that you could do. For example, you could actually transmit something. Let's say this might be a relay, possibly, and receive something. What happens though is that when you transmit, this actually ends up to be interfering with what you are receiving. Yes, any transmission eventually will become an interferer here in full duplex scenarios. Okay, and so yeah, as I said, you could picture something like sensing and transmission at the same time, right? It doesn't really need to change anything about the technology. For example, it's compatible with MIMO, no problem. The issue though is essentially self-interference and other sources of interference. So interference situation becomes way more complicated than we are used to. That's the main problem here. So you see this tries to depict self-interference, right? So it's the same system that interferes with itself, if you want, right? So anything you transmit will interfere potentially, even if you are the one transmitting. So some like applications, as I said, relay. In this case, you have symmetric traffic because you are forwarding what you get. Essentially, it's like right. You don't create new information in the relay. You just forward it. And the channels are asymmetric because you have a different channel for source to relay than from relay to destination, of course. And then you see this red nasty arrow. So whenever you transmit from the relay to the destination, you are actually going to impact what you receive from the source, right? You could have actually two terminals just communicating to each other. For example, D2D, device to device communication. And again, in this case, channels are symmetric between uplink and downlink. Now, uplink and downlink in this case is a bit weird because you have it's more two directions of communication if you have device to device, for example. So think of, sending and receiving. That's probably a better way to say it. And of course, anytime I'm sending something to terminal 2, I'm going to impact my own reception on terminal 1. Yeah, because I'm again transmitting and receiving at the same time and over the same frequency. And you might have stuff like, you might have an access point. Now, you don't have necessarily to choose between serving uplink and downlink user. You can serve both of them, right? You can have at the same time users communicating with you and users you are communicating to. That's possible now. Again, though, you have different sources of interference. So you have the self one again, but you also have, basically user-to-user interference, if you want, right? So you see, let's put it like that. If you have downlink, traditionally what happens? Base station communicates to mobile phone. The only source of interference, because it's all synchronized, right? Another base station will interfere. In uplink, mobile phone transmits to base station. Everything is synchronized, so it can only come from another uplink user. Now it's not true. So you see here an example where user to user is possible, base station to base station is possible, same base station to same base station is possible. And if you have alpha, now we are not assuming this in our work, I'll show later, but you could assume also full duplex at the mobile phone maybe, and then again you could have same mobile phone to same mobile phone. So all over the place, right? So it's clear that the main problem here is interference. Okay. Any question? Comment? So you do have, especially self-interference is very nasty because you know what, it's exactly there. So you are basically competing. So okay, you transmit and this is going to be received at a larger distance. Same with what you receive. So normally the useful signal has traveled quite a bit, but the self-interference is there. So it's huge, okay? So you see this figure that shows you how large it can be compared to the signal of interest. That's why the first thing they immediately did after they came up with the concept was to design self-interference cancellation schemes, because it's something you need. So it could be actually up to 100 plus dB higher than the signal of interest, which is a lot of interference. And the more you target, for example, cell edge users, the more this problem appears, right? Because of course that signal is already kind of very weak, and on top of it you have a tremendous amount of interference. So it could actually be a big bummer for outage performance, right? It could kind of kill all the cell edge users, right? Both in uplink and downlink actually. Now, if you have large dynamic ranges, it starts to be a problem also of the conversion from analog to digital. Okay, because you do need a lot of bits to represent a large dynamics, right? And so that could be a problem. If you have a limitation in the ADC capability, that could become again something that creates trouble. So maybe you have to do some kind of pre-processing so that you can reduce what you give as an input to the ADC. If not, it might become too much to handle. Okay, it's like dealing with the very large dynamics now of range, right, of the signal. Okay. So there are a few things you can do in terms of self-interference cancellation. So one thing is to do passively. So you separate, for example, transmit and receive antennas, so they do not disturb each other too much. Or you might actually do things like playing with geometry. You can put antenna, transmit and receive antennas at the opposite sides, right? So they do not, again, interfere too much. Or you could use beamforming on top of it. You could use directional antennas. So you try, it's like what you do normally with interference, so, but now you focus on self-interference. So for example, if the antennas are kind of close, you should do kind of transmit beamforming in one direction and receive beamforming in another direction. So you minimize again interference, right? These are all things you can think of. Or you can do something more active, which is essentially canceling the interference. So you might just estimate the interference path and subtract it. That's what they do with active cancellation. Or you could actually estimate the self-interference and cancel it at baseband. So you can do actually what we already do for interference cancellation, just that now you have the self-interference part of the story. Now, we are still assuming that you have two antennas though. One for transmission, one for reception, right? It's like in this MIMO thing, we don't say it, but when we say transmit and receive, normally we have two sets of antennas. One is transmitting, one is receiving, right? How about here? Because you still have these. Would it be possible? I mean, you have some situations like relays or sensors where to do full duplex means again you have to transmit and receive at the same time. So one way to do it, of course, is to wait, and I use the same antenna to do both, right? But if this is exactly not the point of full duplex, I want things to happen at the same time, so I need two antennas, one to transmit, one to receive. But maybe that's a problem because for some networks, like maybe sensor networks, it becomes kind of bulky to have two antennas. So would it be possible to have single array doing both? I don't know the answer. I think that's a possible topic of work. And you would have to do probably something more along these lines, right? The active thing. And I know that there was work, I mean, we go back 10 years about parallel interference cancellation. Maybe there are some things you can think of, but yeah, it's not so straightforward, the answer for me at least, okay? Question or comment? Okay, I'm not going too much into the details of this. This is some work we are doing designing actually single antenna, okay, circuitry that, for example, you could use to simultaneously relay and demodulate, okay. It has to do with essentially manipulating the phase difference between transmit and receive signals. So you play with the local oscillator power. This is not published, so we are, this is under review. So we are trying to work out this single antenna full duplex thing. Still not really there. We might actually, there is a plan to try to implement it in the lab and see how it works. So we have some plans in that sense, but at the moment it's a bit more theoretical. It shows some good promise in terms of cancellation, okay. But yeah, this again, in progress. So this, like, actually this lady, she studied in Calcutta. She's from India. She told me it's kind of the oldest engineering school in the country, at least in West Bengal.
Radio physics.
Not radio physics. She studied communication, but like she told me, this department is very, very old.
Radio physics and engineering, Calcutta University.
Possibly. It's like
It's the oldest.
she told me it's the oldest.
That
Yeah.
is the oldest, I guess.
Yeah. I don't know. Don't know.
IIST is not the oldest one.
I don't know.
Electronics department, but radio
I can
physics
ask.
is the oldest
I
department.
can ask her, but it's. Shall we look it up? Let's see where she studied. Then we'll see. Because she told me that. I mean, I don't know. Let's see if she has a Google profile. They told me it's not a very common name in India, right?
Yeah, it is not.
You know it probably, but did you hear about this name before? It's not so common. Yeah, that's what they told me. Maybe this guy. Let's see. She's a very smart and lovely actually lady. So, okay, where did she study? Let's see. Shit. MS degree? No. We missed the interesting bit. Where's the bachelor? I worked. Okay, she worked in a few places. Blah blah blah. Okay, not here then. Maybe here. The CV, huh? Let's see. We'll find out about that. And to open all of them, we'll find something. Okay, this is the lady, first of all. No, same thing as before. Should have asked her. Went back in time. Let's see. Southampton. Blah blah blah. Aha, here we go. West Bengal University of Technology.
Yeah.
You confirm? Is it the oldest one? Probably in West Bengal, I guess she meant. Debatable. Okay, fine. I'll tell her. Anyway, that's where she studied. Okay, so she's the one doing this work on single antenna full duplex. Okay, so okay, good. So once we know more, we'll tell you more about this work. Application scenarios. This is again from some work we are doing and we have under review. As a general rule of thumb, feel free to ask me about publications or stuff like that. We might be able to share things before they're published. I just have to check the rules, but definitely we can point out to the works we have and other works other groups are doing around the world. So my suggestion is send me an email. Try to be specific about what you need. Okay, do not be polite or shy. Just make a list, and then I'll tell you if I cannot do things or I need more time. I'll let you know. But at least you get what you want. Okay, there is no point in being too polite and beating the bush too much. So go to the point. You tell me what you need, and then I might not be able to do it right away, but I'll look into it and I'll give you some pointers as much as I can. Okay, so just ask. Okay, that's the way to get things. You have to ask first, right? So if not, you don't get them. So the scenarios we are thinking of are threefold, kind of. So you could have smart homes. Okay, you could have something like smart grids, or you could have intelligent transportation systems. That's where we are thinking full duplex would be useful. Okay, and so you see, I mean, I don't want to go too much into this, but you have these architectures that have to do with smart grids. So they have this home area network, neighborhood area network. So they have their own terminology for the architecture. Okay, and so you're basically, the target is one of these scenarios. I think the first paper we wrote is about smart grid. So it's exactly about this, how you actually operate, an electric grid in a smart way. So we are comparing here the channel capacity versus SINR. If you have a relay system, or if you don't. So if you don't have a relay system, of course the capacity is going to be lower. And then we try to see if you have half duplex relay, so you have to basically either wait time before you forward information, or you have to use another channel, right? And the capacity is worse than what you can do with full duplex relay, which are the two top curves. There is a bit of influence depending on where the source is. So if you have it closer to the, where the relay is, if you have it closer to the source or closer to the destination, but in general the message is that you can gain quite a lot by doing full duplex relaying, and that's clear, as we said before. You're not wasting resources here, you're just using everything all the time, right? So that's the point. So you get a boost in capacity. So this is something that goes on top of you know, packing more signals because of waveform design, using more antennas, so doing more powerful MIMO, densifying the network, so having, you know, millimeter wave small cells. Full duplex is another way to push the capacity of your system. Yes?
This result, what are the assumptions for the channel state information?
Good question. I think, let me recollect. I can't recollect right now. I mean, I don't think there is some channel state information involved. Yes, it's possibly. I can't be precise now. I'll have to look it up. Yeah, you can, if you send me an email, Kartik, reminding me. I'll find out. Yeah.
And in full duplex system, how are actually in general we are getting this CSM?
Yeah, so one way could be to think about it like sensing. So you could use the receive antenna to do the estimation at the same time you transmit though. So you could keep updating your, right? You could keep updating your channel state information using the receive antenna. So that speeds up things. You can do the things you're normally doing. So it's not that we are changing the assumptions about channel state information, but you're just making things faster and more efficient. You can use your receive antenna at the same time as the transmit antenna, right? One thing that could become more complicated is like the signal level is going down, which is never a good thing. Okay, also probably for estimation, and you have way more interference now, so it could become more complicated even to get a good estimate of the channel. Yeah, but we are not focusing so much on that side of the story, but it is an important aspect. I think you have a good point. Yeah. I'm trying to, I can't remember it right now. I'll look it up. If you remind me, I'll look it up, like the assumptions we have about channel state information. Yeah. So we have another work which was presented a couple of years back in ICC, and this is, so far it's been more, let's say, physical layer. Okay, now we try to take it at the level of system level, and see what happens when you have multiple base stations, multiple mobile phones. So what we are assuming here is like base stations have full duplex capabilities, but users do not. And that's again trying to keep things backward compatible, at least on the user side. We do not want to change the devices really much. Okay, so we are just assuming, you could assume too that you have full duplex at the mobile phone, but we are not doing that. We are just saying the base station can do full duplex. The mobile phones cannot. Okay. So, for example, a full duplex base station can schedule an uplink and a downlink user at the same time on the same frequency channel, right? That's what full duplex is about. Of course, you do increase interference in all directions. So this is a visual representation of what I was saying before. Only one of these guys is actually, you see, only few of these arrows are useful signals, right? You have one in uplink, one in downlink. Anything else in this diagram is interference, okay? Which is way worse than it used to be. You also have self-interference, right? Yeah, so essentially the point about full duplex is it was introduced chiefly to increase spectral efficiency gain. But as a side effect, we increase interference in both directions, which possibly could have, again, as I said before, issues with outage probability. So maybe here you are benefiting the users that are close by, boosting their throughput, but you are maybe punishing the users at the edge of the cell, right? So you have to be careful, you know, how you trade one for the other. So essentially what we try to do is again similar to the work we did on millimeter wave. It's not really so much resource allocation per se, it's more to study the limits of the performance so that we get some indication of what's going on. We do quite a bit of this kind of work in my team. Okay, it's like limits of the network performance. Okay, so it's kind of an input you would give to somebody designing Mac probably. Okay, so we try to see what happens if you have a fraction of the cells that operate in full duplex mode and the fraction that doesn't. So this might be a situation, an initial rollout of 5G, where you have on top of 4G, where you have some base stations that are 5G capable, maybe also full duplex capable, and some are not, and they still have to operate together, right? So we do use stochastic geometry. I'm not going to say too much because we have a lecture next week on that, to characterize this deployment. Now, just for those that are not here next week, stochastic geometry is a tool that has emerged in the past probably 7 to 10 years. So what they do, so there are many models to model how the users are scattered in the environment. Normally what you used to do for base stations was just to have a regular kind of honeycomb, right, deployment. That's not realistic because it assumes a situation better than it is in reality. So when you do these regular deployments, you have actually an overestimation of the actual network performance. On the other extreme of the scale, you have stochastic geometry, which starts to introduce randomness in the way base stations are deployed. So literally the position becomes a random variable. There are some advantages, including the mass tractability and so on. One of the main advantages is that it's closer to the real situation. I don't think it's true that you have base stations deployed so regularly apart, as far as I know, right? It goes with the availability of the real estate and the environment and the requirements. So it's not true that you have this lattice, right? This is good for papers, but in reality, so stochastic geometry, despite being a very mathematical tool, it kind of served a practical purpose in the first place, to become more realistic in the model of base station deployment. Okay, it has been used immensely, really a lot of papers everywhere, and it actually leads to an underestimate of the network performance. It's worse than it is. So the reality is in between, but definitely it gives you a better, let's say, a more conservative worst case scenario picture than the idealized situation. It has its own limitations. I'm going back to that next week, but for those of you that love math, it's a nice tool, very popular nowadays. Maybe too popular in my opinion. They're using it for everything, but it's it actually it is part of the mainstream of theoretical research in 5G, definitely. Okay. So we are trying to see again what we did before for millimeter wave, area spectral efficiency versus coverage trade-offs, and see what happens as a function of how many base stations in our deployment are full duplex enabled, from 0 to 100%. Okay. You could think the 0 to 100% like a rollout set of phases, right? You start from nothing, 5G, up to the point where everything will be 5G. Maybe you can see it that way. So there are a bit more of details about the model. I don't want to spend too much time. So yeah, Poisson process was mentioned before. The stochastic geometry is something that happens in 2D at least. And you generalize the Poisson process to a 2D process. So instead of essentially, so what Poisson process is used for in our field is to measure how frequent is the arrival of information, of packets, right? So it can be much faster than the server capability, much slower, these kind of things. Here we are using it at space level, so in a sense it's more the probability of a node being there over a space, okay, over a region. Anyway, so these are just details, so it's kind of that. So you have some, yeah, you have some base stations that are full duplex, some are half duplex. We are assuming that the user is served by the nearest base station, okay, and we have some probabilities of a base station to be in full duplex mode, downlink mode, or uplink mode. If you have half duplex, you have to declare what you are doing, downlink or uplink. And of course, this is all the base stations we have. So some will be operating both ways, uplink and downlink simultaneously and over the same channel. Some will be just uplink, some will be downlink. Yeah, you can tweak these parameters as you want. So some things about the system parameters we studied. So okay, some. Okay, normally we say that if you have half duplex, you, for example, if you have TDD, we have an equal amount of slots in both links. No power control. That's something could be extended. And we don't have consideration for different channel models for different links. That's a bit shaky as an assumption, in my opinion. That's our work. But you know, we started from something simpler, because if you have user to user, the channel might be very different than if you have base station to base station, which is mostly line of sight, or base station to user, which is partly line of sight. User to user maybe, again, depends on how far you are, right? So there are models for D2D, so that's something we could consider as an extension. Yeah, so I mean, yeah, it's not so much interesting to discuss the parameters. You can look it up. You have, I mean, the paper is cited. Okay. So some results to finish this part of the course. So, okay, here we are looking at area spectral efficiency. So it's like, again, throughput divided by bandwidth divided by the area. Okay. So clearly, if you have a mixed system where this rho f, so this value on the x-axis is the proportion of base stations that are full duplex enabled, 5G base stations you can call them if you want, okay? So if you go from an initial rollout phase where no 5G base station is there, actually the performance is much worse than if you allow all of them to be fully 5G, right, or full duplex, of course. There is some impact of the successive interference cancellation. So basically what you see on the right hand plot is the better SIC capabilities you have, the higher you can push the area spectral efficiency up to some point though. So essentially after 100 dB of successive interference cancellation, you basically do not really benefit too much, because this, I mean, what we are considering here, I should say, is kind of a dense scenario of deployment. So there is still kind of an underlying level of interference, which we can't totally get rid of. So the SIC will cancel the self-interference, but then you have the rest of the interference, which is still kind of nasty. Yes, you have like in the normal situation of half duplex, you never have base station to base station really interference, right? You don't have that. Here you have it. So if you start to deploy cells close to each other, that's a big problem in terms of interference. And self-interference is not meant for that. Then you have to go back. You would have to extend this work to do proper frequency reuse and resource allocation, right? We didn't do that. Okay. Any question?
It will be a typical value of self-interference value in the order.
Yeah, I think it's probably the former slide. It's very high. It's like 50 to 110 dB. Okay, it's larger than the signal of interest. So it's basically interference that is what 10. So 100 dB. What is it? 10 to the 10. It's gigantic, right? So it's like what? 10 billion times bigger. Yes, 100 dB. Yeah, 10 billion times stronger than this sort kind of nasty guy. But you know, they are doing a good job. I mean, I'm not too concerned about that, in the sense that the technology is evolving, so they're doing well in terms of interference cancellation. Okay, self-interference cancellation. Okay, I'm thinking anything else. Okay, then we put the things together, so we see what happens again with the trade-off between area spectral efficiency and coverage. Of course, it's a trade-off. So the trade-off curves, they always look like descending. If you have something going up, it's not a trade-off, right? If you have two things and they are both going up, that's not a trade-off, clearly, okay? But if the curve is coming down, it's a trade-off because you have regions where one is better than the other and so on, right? So clearly, I'm stating the obvious here, probably. So there is, this,
So here this asymmetric additional spectral efficiencies
yeah.
Into 10 power minus 4.
It's very small, yeah, because basically you have to consider one thing. You are.
That means the spectral efficiency is very.
It's not the spectral efficiency. So spectral efficiency is a part of it, and then you divide by the area. So it's a good observation because it's a small value, but the values you have to consider here are you have to compare with other deployments. You can't compare ASC with SC. They are two different things, right? So I can't comment whether this specific value is too good, but it's a new game you're playing, right? So you have, if you have an area, of course, it's a lot of square meters you're dividing by, right? So you have to keep that in mind, yeah.
The coverage is varies from 0.5 to 0.8. What does it mean, coverage?
Coverage basically it's did I define it somewhere or not? Not. I think what we mean is like the probability for a SINR to be higher than some value. Okay, I think I mentioned the threshold here. So is the probability that the SINR in the system is higher than minus 8 dB in this case. Yeah? You can change that, of course. Okay. So what happens? Like if you have downlink, you basically go from, you see that the values are kind of more contained, if you want. And I'm thinking why. So basically downlink means the guy that sees the interference is the mobile phone, right? So interference can come from anywhere, but generally speaking it comes from base stations that are far apart, users that might be close by but they transmit at lower power. So you see the downlink curve is kind of more flat because of this, right? But you could have actually very nasty situations in uplink because you can have interference also from base stations that are close by, okay? And it could actually make a lot of difference. These are mixed systems, so you could have situations where the interferers, this is a system metric. So if you have a mixed situation, what does it mean? In uplink, the interference, the nasty interference will come besides yourself, also from other close by base stations. If they are not active in that specific direction because they are half duplex, you are going to see a big drop in the interference you see. If they are active, it goes up a lot. So it's a situation that is much more variable, right? Kind of makes sense that the curve is, so the area spectral efficiency spans over a larger range, okay? I don't know how much I can convey in a few minutes, but to give you, it's just to give you, some indication of the trends. Now, the main message here, besides these details, is that if you increase the number of transmissions, so essentially you are moving toward the left of these curves. So you see rho f equal 1 means everything is 5G full duplex. So you're going toward that. So what does it mean? If you increase the number of transmissions because of full duplex, you are pushing the area spectral efficiency, but as we said before, you're penalizing the weak users, right? Because you are adding interference to the mix. They're already in trouble, poor guys. And on top of it, you add a lot of interference, so coverage is going to suffer quite a bit with increasing full duplex capabilities. So I think if you have to roll out a 5G network, you have to be careful what you wish for. If it's about few users in good positions, good. If it's about a larger system with users far away, be careful what you do. Maybe you have to provide still some half duplex in the system, yes? So this rho f, you could say it as literally a design parameter you activate at deployment time, because that kind of plays a big difference. So there is a huge difference between different choices of this rho f. So how many base stations of the total should be full duplex enabled? It's a design choice you can make already when you deploy the network, depending on what you want to get. Of course, these are simulations. You might have to check things better, but the good thing about system level simulations, they give you a good indication of what's going on. So this is a good input if you have to deploy the network and see what to do. So you shouldn't, I mean, my point here is you shouldn't deploy a technology blindly, right? That's why these works, in my opinion, are useful, because they give you an indication, be careful. And then you might want to run more precise simulations, drive tests, right? You have to check. But at least, so the point about these studies, and also the one before on millimeter wave, is we are giving kind of a handbook of what is important to consider. And then you have to refine that, but I think these are probably useful messages anyway. More results. I don't want to swamp anybody. We just tried with different powers. Of course, that plays a role. Just the message. Okay, regardless of the figures, you should probably read the paper to understand it better. But so in the case of a half duplex system, there is not so much variation in terms of the area spectral efficiency. Okay, it's essential you avoid these situations where suddenly you have neighbor base stations that interfere with you a lot. They kill you, kind of. Okay, and of course you don't have self-interference, so things are kind of more stable. Densifying the network, you will suffer from interference, but you will not have these drastic changes in performance you see with full duplex. Okay, because full duplex really makes the situation of interference much more unpredictable in a sense. Okay, so now for full duplex system and half duplex system together, so what we call a mixed system, the highest gain you achieve in downlink is when the difference between downlink and uplink transmit power is maximum. So to maximize the downlink gain, you should actually have quite a big difference between uplink and downlink transmit powers. That's what we found. While in uplink, the situation is reversed. You shouldn't have much of a difference between downlink and, again, this is not something you have to consider in normal half duplex systems, but here, whenever you design the transmit signal, you have to think that this is immediately an interfering signal to many different receivers. So there is some tension here, right? So you have to be careful about things. So why in downlink the situation is like that? So let's think about it. So in downlink you are seeing the interference where at the mobile phone, okay, and if I push the base station power a lot, it's going to be not so dramatic because it has to travel a long distance. The user is always going to have a limited power. Here I'm just saying how much more powerful should the base station be. And in downlink, again, I'm seeing the interference at the mobile phone. So the nasty guys are the base stations because they have a lot of power, but they are all kind of far, right? More far away than users, at least, right? Respect to my user. In uplink is reversed. The guy that suffers interference is the receiver always in wireless communication, right? In communication in general. So now you have basically the nasty guys could potentially be very, very close, especially if you have a dense deployment. I'm seeing interference at the base station, but I could have really many around. So that's where I have to be more careful. And maybe I have to kind of be more symmetric, possibly bringing down the base station power in that case. Okay? So you can basically proceed as business as usual in a sense in downlink, but you have to be much more careful in uplink. Okay? Which again is normally the story, right? Uplink is more complicated to deal with because it's not symmetric, the story, right? In cellular communication in general. So okay, so just to sum up, I think we are kind of there with time. Yeah, so basically we did some study about data spectral efficiency and covers both actually for full duplex systems and also before for millimeter waves. So the story of this study is similar to the story before, just different technologies. In this specific case, we saw what happens if you have increasingly more base stations that have full duplex. You could actually replicate similar studies if you want with other technologies. So this could be like a preliminary test to see what happens if you start to deploy more and more capable 5G, right? You could have this kind of study repeated with other capabilities. You can have a mixed system where you have something where you start from 4G, and then you start to see, okay, what happens if this is more for the sake of the guys from the Air Force, but you could possibly do similar thing with 3G and 4G, I guess, right? You could start to see a gradual deployment. I don't know if that's of interest to you, but it's possibly a way to go instead of starting from scratch, right? You could start to see gradually what happens, and I'm sure you could do similar kind of things, actually.
We had a question in our mind that
Yes.
whether the 3G nodes and the 4G nodes can coexist.
The problem is that 4G and 5G are more similar in terms of the radio access, right, technology, because they are sort of relatives of OFDM, kind of. The problem in 3G and 4G is that they use a different technology. It's possibly, though, I mean, I didn't think too much about the problem, but what I know of 3G is very robust to narrowband interference, which is what 4G is, because 4G picks bands, right? So possibly you wouldn't bother too much 3G if you have some portions of the spectrum used by 4G, because 3G is good for these things, right? Unless, of course, you have a OFDM system using all the bandwidth, right? But if you start to use selected channels, possibly not such a big deal.
Basically, we have a core equipment and a RAN of both the system 3G and 4G.
Right.
But what level they will amalgamate? Like if I talk about a SDN, data keeper of the entire user base,